You know what's funny? Astronomers spend billions of dollars building telescopes the size of football fields, launch satellites into space, and coordinate observations across multiple continents, all to essentially take baby pictures. Not just any baby pictures, mind you, but cosmic baby pictures of planets being born. It's like the universe's version of those overeager parents flooding social media with photos of their newborn. Except instead of look at little Timmy's first smile, it's look at this protoplanet accreting matter at 6 billion tons per second. But I have to admit, these are probably the most important baby pictures ever taken. In the summer of 2025, astronomers made a discovery that sent ripples through the scientific community and captured the imagination of space enthusiasts worldwide. They didn't just find evidence of planets forming around distant stars, they caught the process happening in real time, witnessing the very first moments when cosmic dust and gas begin their journey to become worlds. What they saw looks remarkably like what our own solar system must have looked like 4.6 billion years ago, offering us a window into our own origins. On a warm July evening in 2025, Dr. Melissa McClure of Leiden University in the Netherlands sat in her office staring at data that would make history. Her team had been studying a young star called HOPS 315, located about 1,300 light-years from Earth in the constellation of Orion. The star itself wasn't particularly remarkable. It was roughly the same mass and size as our Sun, just much, much younger. At only 100,000 years old, HOPS 315 was practically an infant in cosmic terms. But what surrounded this baby star was extraordinary. Using the combined power of the James Webb Space Telescope and the Atacama Large Millimeter/Submillimeter Array in Chile, McClure's team detected something that had never been seen before outside our solar system: silicon monoxide molecules in the process of condensing from gas into solid minerals. This might not sound like much, but to astronomers, it was like witnessing the moment a caterpillar begins to form its chrysalis. They were watching the very first solid building blocks of planets come into existence. For the first time, we have identified the earliest moment when planet formation is initiated around a star other than our Sun, McClure announced, her voice barely containing her excitement during the press conference that followed. The images were stunning. In vibrant orange, carbon monoxide could be seen blowing away from the star in a butterfly-shaped wind. In brilliant blue, narrow jets of silicon monoxide beamed away from the star like cosmic spotlights. And nestled in between, in a region about the same distance from HOPS 315 as our asteroid belt is from the Sun, the team detected the telltale signature of gaseous silicon monoxide beginning to crystallize into solid silicate minerals. Dr. Merrill Van Hoff of Purdue University, one of the co-authors of the study, put it in perspective. We're seeing a system that looks like what our solar system looked like when it was just beginning to form. It's like a picture of the baby solar system. To truly appreciate what the team had discovered, we need to understand how planets form, a process that's both beautifully simple and mind-bogglingly complex. It's a story written in the language of physics, played out over hundreds of thousands to millions of years, and repeated countless times throughout the galaxy. Stars are born in vast clouds of gas and dust called molecular clouds. These clouds are enormous, some stretch across hundreds of light-years, and contain enough material to make millions of stars. They're also incredibly cold, with temperatures hovering just 10 to 20 degrees above absolute zero. At these frigid temperatures, the gas is mostly molecular hydrogen, with trace amounts of other molecules like carbon monoxide, water ice, and various organic compounds. The clouds appear dark in visible light because the dust particles absorb and scatter starlight. But in infrared and radio wavelengths they glow softly, revealing intricate structures, filaments, clumps and cores, where star formation is beginning or about to begin. When a particularly dense region of one of these clouds begins to collapse under its own gravity, several things happen simultaneously. First, the collapsing material starts spinning. This might seem counterintuitive. Why would gravity cause rotation? The answer lies in the conservation of angular momentum, the same principle that causes a figure skater to spin faster when pulling in their arms. Even if the original cloud was barely rotating at all, any tiny spin gets amplified as the cloud contracts. As the material falls inward, it must conserve its angular momentum, the product of mass, velocity, and distance from the rotation axis. As the distance decreases during collapse, the velocity must increase to keep the product constant. The result is a rapidly spinning object. But there's a limit to how fast something can spin without flying apart. Once the rotational velocity becomes too high, material can no longer fall directly onto the forming star. Instead, it settles into orbit around it, forming a flattened disk. This is what astronomers call a protoplanetary disk, a disk that will eventually give birth to planets. Think of it as a cosmic pizza, with the young star at the center and all the ingredients for making planets spread out in the dough around it. But unlike a pizza, this disk is far from uniform. It's incredibly hot near the star. Temperatures can reach 1,500 Kelvin, about 2,200 degrees Fahrenheit, or higher in the innermost regions, and gradually cools as you move outward, dropping to less than 100 Kelvin in the outer reaches. The disk is also incredibly massive, at least initially. Typical protoplanetary disks contain anywhere from 0.01 to 0.1 times the mass of the Sun. That's roughly 10 to 100 times the mass of Jupiter. Most of this mass is in the form of gas, primarily hydrogen and helium, left over from the cloud that formed the star. But about 1% is in the form of solid particles, dust grains, ice crystals, and eventually the building blocks of planets. And it's in this temperature gradient, this carefully structured environment, that the magic of planet formation begins. The variation in temperature across the disk creates different chemical environments at different distances from the star, allowing different types of materials to exist in solid form at different locations. This is what astronomers call the condensation sequence, a predictable pattern of which materials can survive as solids at which temperatures. Closest to the star, where temperatures exceed 1,500 Kelvin, only the most refractory materials can condense, metals like iron and nickel, and silicate minerals like forsterite and enstatite. These materials can withstand extreme heat without vaporizing. Move a bit further out, where temperatures drop to around 1,000 Kelvin, and other silicates can condense. Further still, at around 700 Kelvin, various sulfides form. But the real game changer happens at what's called the snow line, or frost line, the distance from the star where water can exist as ice rather than vapor. In our solar system, this line was somewhere around 3 to 5 astronomical units from the Sun, roughly in the region where Jupiter now orbits. Inside the snow line, it's too hot for water ice, so rocky materials dominate. Outside the snow line, water ice is stable, dramatically increasing the amount of solid material available for planet building. This is why the giant planets in our solar system are, well, giant. There was simply more solid material available to build them. Even further out, beyond about 30 astronomical units, other volatile materials like methane, ammonia, and carbon dioxide can freeze out, providing even more building material for planets in the outer reaches of the system. The process starts with simple physics, but the details are fiendishly complex. As the disk cools, different materials condense out of the gas phase and into solid particles, like water vapor condensing into dew on a cool morning. But here's where it gets interesting. Different materials condense at different temperatures, and this creates a zonation pattern across the disk. Silicon monoxide is one of these refractory materials. It can only condense at temperatures exceeding 2,200 degrees Fahrenheit. When silicon monoxide molecules floating in the protoplanetary disk cool enough, they bond together to form tiny crystalline grains of silicate minerals, the same minerals that would eventually become major components of rocky planets like Earth. We're talking about grains that are initially just micrometers across, smaller than a speck of dust. But once these first solid grains exist, they become the seeds for everything that follows. The grains can stick together through various processes. At first, when they're still tiny, electrostatic forces dominate, the same kind of static electricity that makes a balloon stick to your hair after you rub it. The grains have slight electric charges and can attract each other, sticking when they collide gently. As grains grow to millimeter sizes, other forces come into play. They can stick together through a process called cold welding, where the molecular forces at the surfaces of the grains bind them together. It's similar to how two pieces of very clean metal can stick together if you press them hard enough. The atoms at the surfaces form chemical bonds. But there's a problem. As particles grow from millimeters to centimeters to meters in size, they enter what planetary scientists call the meter-size barrier. Particles of this size experience significant drag from the gas in the disk, which causes them to lose orbital energy and spiral into the star on timescales of just a few hundred orbits, far too fast for them to grow into planets. For decades, this was a major puzzle in planet formation theory. How do particles get past this barrier? The answer, it turns out, involves several mechanisms working together. One is called the streaming instability. In regions of the disk where there's a high concentration of solid particles, the gas and solids can interact in complex ways that cause the solids to clump together locally. These clumps, once they're dense enough, can collapse directly under their own gravity to form planetesimals, kilometre-sized rocky bodies. Another mechanism involves the trapping of particles in pressure maxima in the disk. The disk isn't perfectly smooth. It has various bumps and wiggles in its pressure profile, caused by turbulence, magnetic fields, or the gravitational influence of already formed planets. Solid particles can get trapped in these pressure maxima, accumulating to high concentrations where they can more easily stick together and grow. Dr. Edwin Bergin of the University of Michigan, another member of the HOPS 315 research team, explained it this way. This is the birth of the seeds of the planets. The story of planetary formation is the story of motion and movement. These tiny grains are constantly moving about in the hot and windy conditions of a young star system, colliding with each other at speeds ranging from gentle taps to high-velocity smashes. Some collisions result in sticking and growth. Others cause fragmentation, breaking particles back down into smaller pieces. It's a delicate balance, and the conditions have to be just right for net growth to occur. Once particles reach kilometre sizes, gravity becomes the dominant force. These objects, called planetesimals, can gravitationally attract other planetesimals and smaller particles. The more mass they accumulate, the stronger their gravity becomes, and the faster they grow, a runaway process that leads to the formation of planetary embryos dozens to hundreds of kilometres across. In the inner parts of the disk, where rocky materials dominate, these embryos eventually collide and merge to form terrestrial planets. Computer simulations suggest that building an Earth-sized planet requires thousands of these catastrophic collisions over tens of millions of years. The final stages of terrestrial planet formation are violent, impacts energetic enough to melt entire planetary surfaces, and in the case of Earth, even to eject material that formed the Moon. In the outer parts of the disk, beyond the snow line, the story is different. Here, there's much more solid material available, thanks to the presence of water ice. Planetary embryos can grow much faster and reach much larger sizes, 10 to 15 Earth masses or more. Once a growing planet reaches this critical mass threshold, something remarkable happens. It becomes massive enough to gravitationally capture hydrogen and helium gas from the surrounding disk. This gas accretion process can be extraordinarily rapid. A planet can double or triple its mass in just a few thousand years, growing from a rocky core to a gas giant in what amounts to the blink of an eye on cosmic timescales. This is how Jupiter and Saturn formed, accumulating massive atmospheres of hydrogen and helium that make up most of their total mass. Their cores, believed to be 10 to 20 Earth masses of rock and ice, represent the embryos that triggered this runaway gas accretion. The first planetesimals in our solar system formed just after the condensation of these crystalline silicate minerals. Some of them grew into terrestrial planets like Earth and Mars, others became the rocky cores of gas giants like Jupiter and Saturn, and some remained small, becoming the asteroids that still orbit the Sun today in the main asteroid belt between Mars and Jupiter. Inside many of these asteroids, and in the meteorites that occasionally break off and fall to Earth, scientists have found these ancient silicate minerals, crystallized 4.6 billion years ago, when our solar system was just beginning. They're like fossils, preserving a record of the earliest moments of planetary formation. Some meteorites even contain microscopic pre-solar grains, dust particles that formed around other stars before the Sun even existed, swept up into the cloud that made our solar system, and preserved within asteroids all this time. Scientists have spent decades studying these meteorites in exquisite detail, using techniques like mass spectrometry to measure the isotopic compositions of different elements. These measurements can reveal the temperatures at which different minerals formed, the timing of various events in the early solar system, and even the presence of short-lived radioactive isotopes that no longer exist naturally on Earth, but which were produced in nearby supernova explosions and incorporated into the solar nebula. Until 2025, these meteorites were the only way to study this crucial phase of planet formation directly. Astronomical observations could detect protoplanetary disks around other stars, and even resolve some of their large-scale structures. But the actual process of particles condensing, sticking together, and growing into planetesimals happened at scales far too small to observe, even with the most powerful telescopes. But now, thanks to HOPS 315, astronomers could watch it happening in real time, 1,300 light-years away. They couldn't see individual particles, of course, those are far too small, but they could detect the spectral signatures of silicon monoxide in both gas and solid forms, revealing that the condensation process was actively occurring. It was like being able to take the temperature of a distant patient. You can't see the molecules directly, but you can infer what's happening at the molecular level from the symptoms you observe. A second discovery, the planet in the gap. Just weeks after the HOPS 315 announcement sent waves through the astronomical community, another team of astronomers made a complementary discovery that added another crucial piece to the puzzle of planetary birth. This time, they didn't just see the ingredients for planets, they photographed an actual baby planet in the act of forming, sitting exactly where theory predicted it should be. The discovery centered on a young star called WISPIT 2, located approximately 5 million light-years away, though astronomical distances are always somewhat uncertain, in the constellation Aquila, the Eagle. The star is only about 5 million years old. In cosmic terms, this is incredibly young. For comparison, if you think of the Sun's current age of 4.6 billion years as equivalent to a 46-year-old human, WISPIT 2 would be about 2 days old. And surrounding this infant star was a magnificent protoplanetary disk with a distinctive and intriguing feature. Multiple concentric rings separated by dark gaps, like a cosmic vinyl record or a series of racetracks circling the star. These ring structures in protoplanetary disks had been observed around many young stars since the Atacama Large Millimeter/Submillimeter Array came online in the early 2010s. In fact, they turned out to be surprisingly common, far more common than astronomers had initially expected. But what causes these rings and gaps? For years, theorists had suggested that they were cleared by forming planets. The idea goes like this. As a growing planet orbits through the disk, its gravity acts like a cosmic vacuum cleaner or snowplow, sweeping up nearby dust and gas. The planet accretes some of this material directly, growing larger in the process. But it also gravitationally scatters other material, pushing it either inward toward the star or outward away from it. The result is a zone around the planet's orbit that becomes depleted of material, a gap in the disk. This process is similar to what happens when you drop a stone into a pond. The stone creates waves that spread outward, and these waves can push floating leaves or debris away from the stone's landing point, creating a clear zone. In the case of planets in disks, the waves are density waves, spiral patterns in the gas that propagate through the disk due to the planet's gravitational influence. Computer simulations of planet formation had been predicting these gap-clearing effects since the 1990s. Theorists could input the properties of a protoplanetary disk, its mass, temperature structure, viscosity, and so on, along with a growing planet, and watch what happened. The simulations consistently showed that once a planet reached a certain mass threshold, roughly the mass of Saturn for typical disk conditions, it would begin to carve a deep gap in the disk. This gap clearing has important implications for planetary evolution. Once a gap forms, it becomes harder for the planet to accrete more material, since it has consumed most of the nearby gas and dust. This can limit how large a planet can grow, potentially explaining why Jupiter and Saturn have the masses they do. The gap also affects the planet's orbit. If there's more material on one side of the gap than the other, the resulting asymmetric gravitational forces can cause the planet to migrate, to move either inward toward the star or outward away from it. Planetary migration is now recognized as a crucial aspect of how planetary systems evolve. It can explain features like hot Jupiters, giant planets orbiting extremely close to their stars, far closer than Mercury orbits the Sun. These planets probably didn't form where they currently reside. It would have been far too hot for them to accumulate their massive gas envelopes so close to the star. Instead, they likely formed further out and then migrated inward, perhaps due to interactions with the protoplanetary disk, or through gravitational interactions with other planets. But while astronomers had seen many disks with gaps, and while the theory of gap opening by planets was well developed and widely accepted, there was a crucial missing piece of evidence. They had never before found direct proof of a planet actually sitting in one of those gaps. The gaps themselves were circumstantial evidence, suggestive but not definitive. Other processes like magnetic fields or dead zones in the disk where turbulence is suppressed could potentially also create ring-like structures. Until now. Using the European Southern Observatory's Very Large Telescope in Chile, an instrument that consists of 4 8.2-meter telescopes that can work together or independently, combined with observations from the Magellan Telescope's MAG-AOX system in the same Chilean desert. The Atacama Desert is one of the best places on Earth for astronomy due to its high altitude, dry air, and minimal light pollution. The international team spotted something extraordinary, a small point of light embedded in one of the gaps in WISPIT 2's disk. At first glance, it might have seemed like just another faint background star, coincidentally aligned with the disk, but careful analysis of its position, brightness, and spectrum revealed that it was something much more interesting, a planet. A baby planet they designated WISPIT 2b, following the exoplanet naming convention where the star gets the designation and planets are labelled with lowercase letters starting with B. Richelle van Kapeleveen, a PhD student at Leiden University in the Netherlands, who led the discovery and was the first author on the paper, could hardly believe what she was seeing when she first identified the planet in the data. Discovering this planet was an amazing experience. We were incredibly lucky, she said in an interview following the announcement. WISPIT 2, a young version of our Sun, is located in a little studied group of young stars, and we did not expect to find such a spectacular system. This system will likely be a benchmark for years to come. The discovery of WISPIT 2b was particularly serendipitous because of how it came about. The team had initially been conducting a survey of young stars with protoplanetary disks, looking for a variety of features and structures. WISPIT 2 was just one target among many, but when they examined the high-contrast images taken with MAG-AOX, which is specifically designed to suppress the bright light from stars and reveal faint objects nearby, they spotted the telltale point source right in the middle of one of the gaps. Follow-up observations confirmed that the point source was moving along with the star, ruling out a background object. Spectroscopic measurements revealed that it was emitting light at wavelengths characteristic of a young, accreting planet. The planet's temperature, estimated from its infrared emission, was around 1000 to 1500 Kelvin, hot enough to glow visibly in the infrared, but not hot enough to be a star. WISPIT 2b is estimated to be about 5 times more massive than Jupiter, making it a gas giant similar to the largest planets in our own solar system. For context, Jupiter is about 318 times more massive than Earth, so WISPIT 2b would be roughly 1,600 Earth masses, a truly massive world. But what makes it truly special isn't just its mass, it's its age and location. At only 5 million years old, WISPIT 2b is one of the youngest planets ever directly imaged. Most of the exoplanets that have been photographed, as opposed to detected through indirect methods like the transit method or radial velocity method, are tens or hundreds of millions of years old, sometimes even older. They've long since finished forming and cooled down considerably. WISPIT 2b, on the other hand, is still in its formation phase, still actively accreting material from its surroundings. And its position within the cleared gap provides the first direct confirmation of something astronomers had long suspected but never proven: that forming planets do indeed create these structures in protoplanetary disks. It's the smoking gun, the definitive evidence linking gaps in disks to planetary formation. Dr. Christian Ginsky of the University of Galway in Ireland, one of the senior researchers on the project and an expert in high-contrast imaging techniques, explained the significance. One might almost think of the planet like a hoover in that sense, sucking up all the dust. It clears out a gap as it orbits because material falls down onto the planet. The discovery was particularly exciting because WISPIT 2b appears to have formed right where it currently sits, what astronomers call in situ formation. There's no evidence that it migrated from elsewhere. The planet's orbit is roughly circular, with no obvious eccentricity that might indicate gravitational interactions with other planets or disk perturbations. Its position in the gap is consistent with a planet that grew up right where we see it, gradually accumulating mass from the surrounding disk and clearing a path as it grew. The images of Wispit 2b showed the planet as a small purple dot against the bright rings of dust surrounding the star. The color in these images is artificial. The observations were made in near-infrared light, which is invisible to human eyes. Astronomers assign colors to different wavelengths to make the structures more visible and easier to interpret. In this case, the rings themselves glowed in white and grey, with the inner ring significantly brighter than the outer one, reflecting the higher density of material closer to the star. The planet sits comfortably in the dark gap between the two most prominent rings, like a child playing in the space between two tires on a playground. But Wispit 2b isn't just sitting there passively. Close examination of the images and follow-up spectroscopic observations revealed that it's actively glowing in a specific emission line called H-alpha, which is produced by hydrogen atoms. This H-alpha emission is a telltale sign that the planet is actively accreting material. Hot gas is falling onto the planet, and as it does so, it heats up and glows. This accretion process is violent and energetic. As gas from the disk spirals down onto the planet, it forms what's called an accretion shock, a region where the infalling material slams into material already on the planet at supersonic speeds. The shock heats the gas to thousands of degrees, causing it to radiate intensely. It's similar to the accretion shocks around young stars, just on a smaller scale. The rate of accretion can be estimated from the strength of the H-alpha emission. For Wispit 2b, preliminary calculations suggest it's accumulating material at a rate of about 10 to the minus 7 to 10 to the minus 6 Jupiter masses per year. That might sound like a tiny amount, and in absolute terms, it is. But remember that these processes operate over hundreds of thousands to millions of years. At these rates, Wispit 2b could potentially double its mass before the disk dissipates, though the accretion rate will likely decrease over time as the disk loses mass and the gap widens. The multi-ring structure of the Wispit 2 disk is also revealing. The presence of at least 3 distinct rings separated by gaps suggests that multiple processes are at work. Wispit 2b is clearly responsible for the gap it sits in, but what about the other gaps and rings? They could indicate the presence of additional planets that haven't yet been detected, perhaps smaller, fainter objects that are below the detection threshold of current instruments. Alternatively, the rings could be shaped by a combination of planetary influence and other disk processes, like pressure bumps caused by opacity transitions, regions where the disk's ability to absorb and emit light changes, or magnetically dead zones. Future observations with more sensitive instruments, particularly the upcoming James Webb Space Telescope observations planned for this system, should be able to determine whether there are additional planets lurking in the other gaps. If so, Wispit 2 could turn out to host an entire planetary system in the making, a solar system being born before our eyes. The Wispit 2 system is particularly valuable for another reason. It's relatively nearby, at least by astronomical standards. While 5 million light-years sounds like an enormous distance, and it is, certainly beyond anything humans could ever hope to travel to, it's actually quite close compared to many other star-forming regions. This proximity means astronomers can observe it in great detail, resolving structures on scales of just a few astronomical units, comparable to the orbits of the inner planets in our solar system. This level of detail is crucial for understanding the physics of planet formation. Astronomers can measure the temperature structure of the disk, the distribution of different molecular species, the kinematics of the gas, how it's moving, and the properties of the dust grains, all with unprecedented precision. They can watch how material flows through the disk, how it accumulates onto the planet, and how the planet's gravity sculpts the disk structure. It's like having a working laboratory, where the experiments take hundreds of thousands of years, but we can observe them in exquisite detail. The team's discovery paper, published in the astrophysical journal Letters in August 2025, included not just the detection of the planet, but also detailed modeling of the disk structure. By comparing the observations to computer simulations of planet-disk interactions, they estimated that Wispit 2b
has been clearing its gap for at least several 100,000 years, roughly 10% of the disk's total age. This timescale is consistent with theoretical predictions and provides important constraints on models of planet formation. Watching a rogue planet throw a tantrum. As if two groundbreaking discoveries weren't enough, October 2025 brought yet another twist to the story of planetary formation. Astronomers studying a rogue planet, a world wandering through space without a parent star, witnessed it undergoing what can only be described as a cosmic growth spurt. The planet in question, with the catchy designation CHAR 1107-7626, had been known since 2008. Located in the Chameleon constellation, it's a massive world, somewhere between 5 and 10 times the mass of Jupiter. But unlike most planets, CHAR 1107-7626 doesn't orbit a star. It's a wanderer, a cosmic orphan drifting through interstellar space, except it's not quite alone. Like a young star, CHAR 1107-7626 is surrounded by its own disk of dust and gas. This had puzzled astronomers for years. How could a planet have such a star-like disk? The answer, it turns out, reveals something profound about how planets can form. In the fall of 2025, observations from the European Southern Observatory's Very Large Telescope and the James Webb Space Telescope revealed that CHAR 1107-7626 was in the middle of a feeding frenzy. The planet was accumulating material from its surrounding disk at an astonishing rate, about 6 billion tons per second. That's 8 times faster than it had been growing just a few months earlier, making it the strongest growth rate ever recorded for any planet of any kind.
Dr. Ray J. Awardiner, Provost of Johns Hopkins University and a senior author on the study, described the scene. "We've caught this newborn rogue planet in the act of gobbling up stuff at a furious pace. Monitoring its behaviour over the past few months, with 2 of the most powerful telescopes on the ground and in space, we have captured a rare glimpse into the baby phase of isolated objects, not much heftier than Jupiter. Their infancy appears to be much more tumultuous than we had realised." The discovery challenged conventional thinking about planet formation. Traditionally, planets are thought to form in disks around stars, with the star providing the gravitational anchor and much of the heat that drives the formation process. But CHAR 1107-7626 seemed to be forming more like a star itself, from a contracting cloud of gas and dust, complete with its own accretion disk. Dr. Alex Scholes of the University of St Andrews, a co-author of the study, put it in perspective. "We're struck by quite how much the infancy of free-floating planetary mass objects resembles that of stars like the Sun. Our new findings underscore that similarity and imply that some objects, comparable to giant planets, form the way stars do, from contracting clouds of gas and dust, accompanied by disks of their own, and they go through growth episodes, just like newborn stars. At between 1 and 2 million years old, CHAR 1107-7626 is still very much in its infancy. The growth spurts the planet experiences appear to be episodic. The planet grows relatively slowly for periods, then suddenly goes through rapid accretion events where it sucks up material at tremendous rates. These bursts might be triggered by instabilities in the disk, or by the planet's magnetic field suddenly becoming more efficient at channeling material onto the planet. The researchers noted that CHAR 1107-7626 had experienced a similar high growth rate event in 2016, suggesting that these spurts might be a regular part of the planet's development. This raised fascinating questions. How long do these bursts last? How often do they occur? And most importantly, what do they tell us about the planet formation process in general? Together, these 3 discoveries, HOPS 315's condensing minerals, WISPIT 2b in its gap, and CHAR 1107-7626's growth spurts, paint a picture of planet formation that is both more detailed and more complex than scientists had previously imagined. They represent snapshots at different stages of the planetary birth process, allowing astronomers to piece together a more complete timeline of how worlds come into being. The HOPS 315 observations provide the starting point, the moment when gas begins to condense into solid particles. This is time 0 for planet formation, the instant when the raw materials for worlds begin to take physical form. Without this step, nothing else can happen. No particles mean no pebbles, no rocks, no planetesimals, no planets. It's the foundation upon which everything else is built. The significance of catching this moment cannot be overstated. Before HOPS 315, astronomers had only indirect evidence of this process from meteorite studies. They could see the end products, the crystalline minerals in ancient meteorites, but they couldn't watch the process happening. It's like trying to understand baking by only examining the finished bread, without ever seeing flour, water, and yeast combine and transform. Now, for the first time, they could observe the cosmic kitchen in action. The fact that this condensation happens in a region of the disk at about the same distance from the star as our asteroid belt is from the Sun is particularly intriguing and significant for multiple reasons. First, it suggests that in our own solar system, the first solids formed at similar distances from the young Sun, roughly 2 to 4 astronomical units. These materials would have provided the building blocks not just for the asteroids that remain in that region today, but also for the terrestrial planets. The physics of why condensation occurs at this distance relates to the temperature gradient in the disk. Close to the star, it's simply too hot for even the most refractory materials to solidify. Further out, temperatures drop below the condensation points of various materials. Silicon monoxide, being one of the hottest condensing materials, forms first and closest to the star. This creates a supply of solid building blocks at just the right distance to eventually form rocky planets. Some of these early minerals might have been transported inward through various dynamical processes, perhaps dragged along by the flow of gas in the disk, or scattered inward by gravitational interactions with larger planetesimals to contribute to Earth's formation. Others moved outward, eventually seeding the cores of the gas giants Jupiter and Saturn. The asteroid belt, where many of these primitive materials remain today essentially unchanged, serves as a museum of this earliest era of solar system formation. Dr. Logan Francis, a postdoctoral researcher at Leiden University and a co-author on the HOPS 315 study, highlighted this connection. We're really seeing these minerals at the same location in this extrasolar system as where we see them in asteroids in the solar system. This gives us confidence that we're watching a process that occurred in our own cosmic backyard billions of years ago. It's like having a time machine that lets us observe our own origins. This parallel between HOPS 315 and the early solar system extends beyond just the location of mineral formation. The composition of the condensing materials, the temperature at which they form, the rate at which they accumulate, all of these match what we know from meteorite studies. It's a stunning confirmation that the processes we see happening in HOPS 315 are not just analogous to, but are actually the same as what happened when Earth and the other planets of our solar system were forming. The WISPIT 2b discovery shows us what happens next in the sequence. Once enough solid material has accumulated in the disk, once particles have stuck together and grown from microscopic grains to meter-sized boulders to kilometer-sized planetesimals, gravity takes over as the dominant force. Small objects merge into larger ones, which merge into even larger ones. Eventually, these objects become massive enough to start fundamentally altering the structure of the disk around them. This is what we see with WISPIT 2b. The planet, now 5 Jupiter masses and still growing, has swept clean the region around its orbit. Material that used to be there has either fallen onto the planet, been scattered away by gravitational interactions, or migrated inward or outward to accumulate in the rings we see on either side of the gap. The gap itself is a testament to the planet's gravitational dominance over its orbital zone, one of the key criteria that defines what it means to be a planet, according to the International Astronomical Union's 2006 definition. The multi-ringed structure of the WISPIT 2 disk, with WISPIT 2b sitting in one of the gaps, also suggests a possibility that's both exciting and profound. Multiple planets might be forming in this system simultaneously. Each gap could potentially harbour an additional planet, though only WISPIT 2b has been directly detected so far. The inner rings might be sculpted by a smaller, rocky planet forming closer to the star. The outer rings could indicate the presence of another gas giant, perhaps still in an earlier stage of formation than WISPIT 2b. If true, this would make the WISPIT 2 system remarkably similar to our own solar system, which has 4 terrestrial planets: Mercury, Venus, Earth, Mars, an asteroid belt, and then 4 gas and ice giants: Jupiter, Saturn, Uranus, Neptune, further out. The architecture of our solar system, small, rocky worlds inside, giants outside, is thought to reflect the structure of the protoplanetary disk from which it formed, with the snow line serving as a major dividing point. The Char 1107-7626 observations add a crucial twist to the story, one that challenges some of our preconceptions about how planets grow. They show that planet formation isn't always a smooth, gradual process of steady accumulation. Instead, it can be punctuated by dramatic events, growth spurts where a forming planet suddenly doubles or triples its accretion rate, gobbling up material at phenomenal speeds before settling back down to a slower, steadier pace. Think of it like human growth. Children don't grow at a perfectly steady rate. Instead, they go through growth spurts, periods where they might shoot up several inches in just a few months before the growth rate slows down again. The same appears to be true for forming planets, at least for some of them. These growth spurts might be triggered by various mechanisms: instabilities in the accretion disk, changes in the magnetic field structure, interactions with other forming planets, or the sudden arrival of a clump of material that had been accumulating elsewhere in the disk. Understanding these growth spurts could help explain some puzzling features of our own solar system. For instance, why are Jupiter and Saturn so much more massive than Uranus and Neptune, despite all four being gas ice giants that formed in similar parts of the disk? The traditional explanation involves the timing of their formation relative to the dissipation of the gas disk. Jupiter and Saturn formed first and fastest, accumulating massive gas envelopes before the disk's gas was depleted. Uranus and Neptune formed later, or more slowly, so by the time they reached the critical core mass to trigger runaway gas accretion, most of the gas was already gone. But the growth spurts observed in Char 1107-7626 suggest an alternative or complementary explanation. Perhaps Jupiter and Saturn experienced more frequent or more powerful growth spurts, allowing them to accumulate more gas before the disk dissipated. Or maybe Uranus and Neptune formed at locations in the disk where growth spurts were less likely to occur. The episodic nature of accretion, with its bursts and lulls, adds a layer of stochasticity, randomness, to planet formation that could help explain why no two planetary systems are exactly alike. The technology making it all possible. None of these discoveries would have been possible without the extraordinary technological achievements of modern astronomy. The James Webb Space Telescope, launched in December 2021, has proven to be a game-changer for studying protoplanetary disks and planet formation. Webb's massive 6.5-meter mirror and its suite of infrared instruments allow it to peer through the thick clouds of dust that surround young stars. Visible light gets scattered and absorbed by dust, but infrared light can pass through relatively unimpeded. This makes Webb ideal for studying the hot inner regions of protoplanetary disks, where the first minerals condense. In the HOPS 315 observations, Webb detected the infrared signatures of silicon monoxide molecules. These molecules emit light at specific wavelengths as they vibrate and rotate, creating a spectral fingerprint that astronomers can identify. By analysing the strength and shape of these spectral features, the team could determine not just that silicon monoxide was present, but also its temperature, velocity, and abundance. But Webb couldn't do it alone. The Atacama Large Millimeter/Submillimeter Array, or ALMA, provided crucial complementary data. Located high in the Chilean Andes at an altitude of 16,500 feet, ALMA consists of 66 radio dishes that work together as a single, massive telescope. While Webb observes in the infrared, ALMA observes at longer, millimeter wavelengths. These longer wavelengths are perfect for studying cooler material and for mapping the distribution of molecules throughout protoplanetary disks. In the HOPS 315 observations, ALMA detected jets of silicon monoxide streaming away from the star at high velocities. By comparing the amount of silicon monoxide in these jets to the amount expected based on the gas composition, the team could infer that some of the gaseous silicon monoxide was condensing into solid particles, indirect but compelling evidence of mineral formation. The synergy between Webb and ALMA exemplifies how modern astronomy works. Different telescopes, observing at different wavelengths, provide complementary pieces of information that together create a complete picture. It's like the parable of the blind men and the elephant.
Each telescope alone would give a limited view, but together they reveal the full truth. For the WISPIT 2b discovery, the key technology was the MAG-OX Extreme Adaptive Optics system on the Magellan Telescope. Adaptive optics is a technology that corrects for the blurring effects of Earth's atmosphere. As starlight passes through the turbulent air above the telescope, it gets distorted, causing stars to twinkle and images to blur. Adaptive optics systems use a deformable mirror that can change its shape hundreds or thousands of times per second, compensating for atmospheric distortions in real time.
MAG-AOX takes this concept to the extreme, using cutting-edge technology to achieve some of the sharpest images possible from a ground-based telescope. Combined with coronagraphic techniques that block the bright light from the star itself, MAG-AOX allowed astronomers to see the faint glow of WISPIT 2b, even though the planet is millions of times dimmer than its parent star and sits right next to it in the sky. Implications for exoplanet science. These discoveries have profound implications for our understanding of planetary systems beyond our own. Over the past 3 decades, astronomers have discovered more than 5,000 exoplanets orbiting other stars. These worlds come in a bewildering variety. Hot Jupiters orbiting closer to their stars than Mercury orbits the Sun, super-Earths with no analogue in our solar system, ice giants, ocean worlds, and everything in between. But almost all of these exoplanets are mature worlds, billions of years old. They've long since finished forming and have settled into stable orbits. Studying them is like trying to understand human development by only looking at adults. You can learn a lot, but you miss crucial information about how they grew and changed over time. The new observations of HOPS 315, WISPIT 2b, and CHA 1107-7626 are like having ultrasound images of a developing fetus. They show us planets in the act of formation, capturing processes that last only a few 100,000 years, a cosmic eye blink, but which determine the final characteristics of the planets that emerge. One of the biggest questions in exoplanet science is, why are planetary systems so diverse? Our solar system has a particular architecture: small rocky planets close to the Sun, giant gas planets further out, and icy bodies in the outer reaches. But many exoplanetary systems look nothing like this. Some have giant planets extremely close to their stars. Others have planets packed so tightly together that they'd be gravitationally unstable in our solar system. Understanding the earliest stages of planet formation is crucial to answering these questions. The initial conditions in the protoplanetary disk, how much material there is, how it's distributed, what it's made of, set the stage for everything that follows. Differences in these initial conditions, perhaps caused by the star's mass, its environment, or random chance, could lead to the diversity we see in mature planetary systems. The HOPS 315 observations are particularly valuable because they show that the first solid materials form at similar locations across different stellar systems. This suggests that at least some aspects of planet formation are universal, governed by fundamental physics rather than unique circumstances. The temperature gradient in protoplanetary disks determines where different materials condense, and this gradient is set by the star's luminosity and the disk's properties, both of which follow predictable patterns. The WISPIT 2b discovery confirms that planets clear gaps in disks as they form, a prediction made by theorists decades ago, but never before directly observed. This process is thought to be crucial for the formation of gas giants. As a planet grows, it begins to dominate the gravitational environment in its orbital zone. It accretes material from within the gap, growing larger and eventually accumulating a massive atmosphere of hydrogen and helium from the surrounding disk. Interestingly, the gap-clearing process also has implications for terrestrial planet formation. As gas giants form in the outer parts of the disk, they can influence the distribution of material in the inner regions where rocky planets form. In our solar system, Jupiter's early formation might have prevented a planet from forming in the asteroid belt region by stirring up material and preventing it from coalescing. Jupiter's gravitational influence might also have shepherded water-rich material from the outer solar system into the inner regions, providing Earth with the water that makes life possible. The CHA 1107-7626 observations
suggest that planets can form through multiple pathways. While most planets probably form in disks around stars, some objects of planetary mass might form directly from collapsing gas clouds, more like stars than traditional planets. These sub-brown dwarfs, or planetary mass objects, blur the line between planets and stars, challenging our definitions and expanding our understanding of how worlds can come into existence. Looking to the future. The discoveries of 2025 represent just the beginning of a new era in planet formation studies. As telescopes become more powerful and observation techniques more sophisticated, astronomers expect to witness planet formation in ever greater detail. The James Webb Space Telescope, though only a few years into its mission, has already revolutionized the field. Future observations will target more protoplanetary disks, building up a statistical sample of systems at different stages of formation. By studying dozens or hundreds of systems, astronomers will be able to identify patterns and outliers, distinguishing between universal processes and special cases. ALMA is also being upgraded with new receivers and capabilities that will allow it to observe fainter objects and detect more subtle spectral features. These improvements will enable the study of smaller, lower-mass disks around low-mass stars, the most common type of star in the galaxy, and prime candidates for harboring potentially habitable planets. Ground-based telescopes are also getting more powerful. The European Extremely Large Telescope, currently under construction in Chile, will have a mirror 39 meters in diameter, about 6 times larger than Webb's mirror and 4 times larger than any current optical telescope. With such enormous light-gathering power and cutting-edge adaptive optics, the ELT will be able to directly image smaller, younger planets and study their atmospheres as they form. Dr. Ginsky, reflecting on the rapid pace of discovery, noted, "We were so fortunate to have these incredible young researchers on the case. This is the next generation of astrophysicists who I am sure will make more breakthrough discoveries in the years to come." Indeed, many of the key discoveries of 2025 were led by early career scientists, PhD students and postdoctoral researchers who brought fresh perspectives and enthusiasm to challenging problems. Van Kapeleveen, who led the Wispit 2b discovery while still working on her doctorate, and other graduate students who participated, described the work as career-defining and mind-blowing. Future observations will also benefit from machine learning and artificial intelligence. As the volume of astronomical data grows exponentially, human astronomers can no longer examine every image or spectrum manually. Machine learning algorithms can be trained to identify interesting objects or unusual features automatically, flagging them for detailed follow-up study. These AI tools are already being used to discover exoplanets in data from NASA's TESS mission, and to identify gravitational lenses in surveys of millions of galaxies. Connecting to the search for life. While the 2025 discoveries focused on the early stages of planet formation, they have important implications for the search for life beyond Earth. After all, before a planet can host life, it has to form in the first place. And the conditions during formation, what materials are available, where the planet forms in the disk, how quickly it grows, all affect whether that planet will ultimately be habitable. The detection of silicon monoxide condensing around HOPS 315 is particularly relevant. Silicate minerals are major components of rocky planets like Earth, but they're not the only ingredients needed for a habitable world. To support life as we know it, a planet also needs water, organic compounds, and a stable climate. Water, in the form of ice, is abundant in the outer parts of protoplanetary disks, but rare in the hot inner regions where terrestrial planets form. Understanding how water gets from the outer disk to the inner planets, perhaps through the migration of icy planetesimals or through chemical reactions on mineral surfaces, is crucial for understanding where habitable planets can form. Organic compounds, the complex carbon-based molecules that serve as the building blocks of life, also form in protoplanetary disks. Observations with Webb and other telescopes have detected a rich array of organic molecules in disks, from simple methane and carbon dioxide to more complex hydrocarbons. These molecules can be incorporated into forming planets, providing the raw materials for biochemistry if conditions are right.
The timing of planet formation also matters. If a terrestrial planet forms too early, before the disk's gas has dissipated, it might accumulate a thick hydrogen-helium atmosphere that never goes away, turning it into a mini Neptune rather than a rocky world. If it forms too late, after the disk has dispersed, there might not be enough material left to build a substantial planet. The observations of HOPS 315 and WISPIT 2b help pin down these timescales, showing that planet formation begins remarkably early and proceeds rapidly. Furthermore, the discovery of rogue planets like CHAR 1107-7626 raises intriguing questions about habitability. Could a rogue planet, wandering through interstellar space far from any star, ever support life? Probably not on its surface, which would be frozen solid without a nearby star for warmth. But if the planet is massive enough to have a thick atmosphere and geological activity, it might have a subsurface ocean kept liquid by tidal heating or radioactive decay. Some scientists speculate that such worlds could be surprisingly common, outnumbering planets orbiting stars, and that they might even harbour life in their hidden oceans. The wonder of cosmic creation. As we wrap up this journey through the latest discoveries in planet formation, it's worth stepping back to appreciate just how remarkable this all is. We live in an era when humans can observe events happening thousands of light years away, watch planets being born around alien stars, and piece together the story of our own origins. Think about what the astronomers observed around HOPS 315. That light left the star 1,300 years ago, during the European Middle Ages. It travelled across the vast emptiness of space for more than a millennium, carrying within its wavelengths the encoded information about silicon monoxide molecules condensing into minerals. And in 2025, that light arrived at Earth, where it was captured by a telescope orbiting 1 million miles from our planet and analysed by scientists who decoded its message. The whole process, from the photon leaving the molecule to the scientific paper being published, connected the 8th century and the 21st century, bridged the vast distances of interstellar space, and united the fundamental physics happening around a baby star with the curiosity and ingenuity of the human mind. And what these observations revealed is that the process happening around HOPS 315 is the same process that happened in our own solar system 4.6 billion years ago. The silicon monoxide condensing into silicates around that distant star is the same as the silicates that condensed around the young sun. Some of those ancient silicates eventually became part of the planetesimals that merged to form Earth, which means that the very atoms making up our planet, the silicon in sand, the oxygen in air, the iron in our blood, once condensed out of a hot disk of gas and dust surrounding a young star, just like we're seeing around HOPS 315. This realization connects us, in a very real and physical way, to the stars and to the cosmic processes that create worlds. We are not separate from the universe, observing it from the outside. We are part of it, made of the same materials, shaped by the same forces. Every atom in our bodies was forged in the heart of a star, or created in the Big Bang. Every molecule in our cells follows the same laws of physics and chemistry as the molecules condensing in protoplanetary disks light years away. The discoveries of 2025 remind us that planet formation is not a rare or special event. It's a natural, inevitable consequence of how the universe works. Give a young star a disk of gas and dust, wait a few 100,000 years, and you'll get planets. The specifics might vary, different masses, different compositions, different orbits, but the basic process is universal. And if planet formation is universal, then planets must be everywhere. The Milky Way galaxy contains an estimated 200 to 400 billion stars. If even a fraction of them have planets, and current evidence suggests most stars do, then there could be hundreds of billions of planets in our galaxy alone. And there are hundreds of billions of galaxies in the observable universe. The numbers become almost meaningless at this scale, but the implication is clear. We live in a universe full of worlds. Some are scorching hot, some frozen cold. Some are massive gas giants, some tiny rocky worlds. Some orbit close to their stars, some far away. Some are alone, wandering through interstellar space. but they're all planets, all formed through the same fundamental processes we're now beginning to understand in detail. And if planets are everywhere, what about life? We still don't know whether life is common or rare in the universe. It might be that given the right conditions, liquid water, organic compounds, energy sources, stable environments, life emerges readily. Or it might be that life requires such a specific and unlikely combination of circumstances that it's vanishingly rare. But thanks to discoveries like those of 2025, we're getting closer to answering that question. By understanding how planets form, where they form, and what they're made of, we're learning which worlds are likely to be habitable and where we should focus our search for extraterrestrial life. The baby planets being born around HOPS 315 and WISPIT 2 won't be habitable for billions of years, if ever. But somewhere in the galaxy, there are probably planetary systems at every stage of development. Some are just beginning, like the ones we observed in 2025. Others are in their middle age, like our solar system. And still others are ancient, with planets that formed when the universe was young, and which might have hosted civilizations that rose and fell long before Earth even existed. We're part of this cosmic story, inhabitants of one world among countless others, observers trying to understand the grand drama of creation playing out across the universe. The discoveries of 2025 are chapters in that story, revealing how planets, and perhaps life, come into being. And there you have it, folks, the remarkable story of how astronomers in 2025 witnessed the birth of planetary systems for the first time, catching the universe in the act of creating new worlds. From the condensing minerals around HOPS 315 to the baby planet WISPIT 2b nestled in its gap, to the growth spurts of the rogue planet CHA 1107-7626, we've seen cosmic processes that echo the birth of our own solar system, billions of years ago. These discoveries represent more than just scientific achievements. They're windows into our own origins, showing us where we came from and reminding us that we're made of the same stuff as stars and planets across the universe. As telescopes become more powerful and observation techniques more sophisticated, we can only imagine what other cosmic wonders await discovery. Thank you so much for listening to this journey through the latest frontiers of astronomy and planet formation. If you enjoyed this story and want to hear more about the amazing discoveries happening in space science, please consider subscribing to stay updated with the latest cosmic news and insights. Until next time, keep looking up at the stars and wondering about the countless worlds being born among them. Clear skies, everyone.